Good afternoon, everyone. Today I will present our photosynthesis final project. Let me start with background and motivation. We all know the principle of standard deviation. When the sequence length grows, attention quickly became the bottleneck. Therefore, we need to find a IO-efficient attention algorithm that maps well to resource-limited platform like FPGA or edge device. As I just mentioned, standard attention suffers from a quadratic complexity in the sequence length T. We not only have to compute the 4 T by T score matrix, we also have to store and move that matrix and the softmax weights in and out of memory. As a result, the performance is dominated by memory traffic between HBM and on-chip buffer. On top of that, the repeated data movement also makes long context processing essentially impractical on small resource-constrained devices. FlashAttention addresses this by being explicitly I/O aware. First, it uses the tiling strategy. Instead of forming the 4 T by T matrix, it processes attention on a small tail that feeds entirely on-chip SRAM. Second, it uses an online softmax. By keeping a rounding maximum and a rounding normalization, we can compute softmax incrementally without storing the full matrix. Third, the backward pass. FlashAttention simply recomputes the attention score inside each tail instead of reading and writing them back twice. Next, I will give a simple quantified I/O analysis to make this iteration more quantitative. We will compare the memory traffic of standard attention and FlashAttention, and then look at what that implies for operational intensity on hardware. For standard attention, both the QKV computation and the softmax scale roughly at square of t, where t is context length. More importantly, the memory traffic is also quadratic in t. We load QKV, we read and write the 4 large t by t score matrix, and we read and write the attention weights, and finally we write out the output. So if you sum all of this term up, the total memory traffic is on the order of t squared, which is extremely large. So the standard attention is clearly memory intensive and memory bound. For FlashAttention, the compute cost stays the same. We still have to compute attention score. However, the memory access pattern changes dramatically. We only load QKV once, and we never materialize the score matrix in memory, and we never store and read the attention weight. The only thing we write back is the final output. As a result, the total memory traffic dropped by about from like proportional to t squared to linearly in t. So when t is extremely large, which is common in modern day models, FlashAttention reach a much higher operational intensity, effectively solving the memory bound nature of standard attention. This slide here shows the operational intensity behavior of FlashAttention on several commonly used large language model. On the right side, you can see the simplified formula. As shown here, you can see that this ratio tells us how FlashAttention improves the operational intensity compared to standard attention. It depends mainly on sequence length t and the head dimension h. Because modern-day LLM tends to use very long context window, while keeping the head dimension relatively small, this ratio can become very large. The table below lists several representative commercial and open source model, and we can see that if we plug in the values into the formula, especially for long context lengths like 8,000 tokens or even 128,000 tokens, we get a very large T, and like as a result, for a typical small commercial model, FlashAttention can increase operational intensity by roughly 64 times. In other words, it is a very great method that changes a memory bound operation to a high intensity compute bound operation, which is exactly what modern day hardware like FPGA and GPUs can take advantage of.
Hello everyone, my name is Hao, and now I'm going to present the FlashAttention baseline detail. FlashAttention is basically an optimized version of the standard scale dot product attention that will reduce both the time and memory cost by avoiding explicit materialization of the full QK transpose matrix. In our implementation, the input Q, K, and V activations for all batches, timestamps, and heads are stored in a flat global array. For each batch and head, we iterate over the query tiles, load only a small portion of the queue, and initialize rounding softmax staticity M and I together with an output accumulator O. We then swap over the key values tiles. For each tiles, we load the corresponding K and V blocks and compute a local score matrix S. Then we will update M and L using the online softmax formulas to stay numerically stable across the tiles, and accumulate the appropriately rescale PV contribution into O. And after all KV tiles have been processed for the given query tile, then we will perform a final normalization O per row and write the finished output back to the global memory. And now, just let me go through some implementation details of how we use HLS to optimize our FlashAttention design. These are the 4 key HLS optimization that we do for our design, and let me go through this one by one. The first optimization is loop pipelining and also unrolling. So for most inner loops, such as the low stored loops and also the mammal and softmax loops, we apply the pipeline II equal to 1 so that the design will accept a new iteration every clock cycle. This will ensure really high throughput for the entire system. And at the same time, that will intentionally limit the amount of parallelization by setting the unroll factor equal to 2 for the dot product and output update loops. This is because in our early versions of the design that we use a more aggressive unroll factor of 4, which will create a deeper combinational path and eventually leads to a timing violation in the Z board. The second optimization was about array partitioning. So to support the partial unroll loops, they will also adjust the memory organization using the HLS array partition. So for the 2D tiles, buffers such as Q tile, K tile, V tiles, and O tiles, and also the temporary local tiles using the low store, we apply cyclic partitioning along the feature dimension, which is dimension equal to 2, with the sand factor as the unroll. So this will effectively split each row of the tiles into multiple small banks, allowing 2 independent reads or writes to process in a parallel without port conflicts. For small 1D arrays such as MVAC and IVACs, as well as the temporary score matrix S tile, we use complete partitioning, which applies each element into its own register or small lookup trap. This completely removes multiplexer on those arrays, giving the scheduler maximum flexibility and also help to reduce the routing congestion and timing pressure on the critical paths of the online softmax and also accumulation logic. The third optimization that I want to talk about is about expression balancing and also inlining control. So disabling inline will keep the function as a separate scheduling unit in HLS tools, which helps with timing closure by preventing the entire design being flattened into one huge block. The expression balancing pragma will instruct the tools to reshape long arithmetic expression, such as dot products, and also the accumulation of exponentials into a more balanced adder tree. The last optimization is how do we pipeline data movement and also streaming interface. So on the I/O side, that we apply pipelining to the memory movement function and use lightweight streaming interface at the top levels. Both the write mem and read mem are fully pipelined with II equal to 1, so the design can ingest and emit 1-bit words per clock cycle and keep the external string fully usualized. This combination of pipeline DMA style memory access and streaming interface will ensure that FlashAttention compute core is not starved by IOs and can be clearly integrated with a larger accelerated pipeline on the Z board.
Hi, I'm Wenbo. Next, I will present the performance and resource utilization results. For our design, both standard attention and FlashAttention match the float 32 golden reference within 1E-3 numerical tolerance, with no observed mismatches. One interesting observation is that the unoptimized FlashAttention baseline is actually slower than standard attention, with 2.86 million cycles versus 1.84 million. There are two main reasons. First, ideal on-chip memory simulation. In standard attention, the dominant bottleneck should be memory I/O since it materializes an n-squared score matrix. But in HLS, we simulate this memory using BRAM on FPGA with zero excess latency, which masks the real I/O bottleneck. As a result, standard attention looks artificially faster. Second, additional compute control overhead in FlashAttention. FlashAttention performs block-wide softmax and maintains running statistics. Although mathematically it has the same flops as standard attention, the actual control logic increased latency when not optimized. And for the optimization impact, after applying hardware-aware optimization like pipelining and control unrolling, FlashAttention becomes compute efficient and exposes parallelism properly. And this results in 13.6 times speed up over standard attention and 21.2 times speed up over the unoptimized FlashAttention baseline. And for the memory efficiency, even after optimization, FlashAttention still uses significantly less VRAM. This is because it processes attention intels and never materialize the full n-squared score matrix. In summary, optimization unlocks FlashAttention's real hardware advantage. Next is the conclusion part. Here, I will summarize our key findings from this project. First, for the algorithm hardware co-design. The main challenge is that algorithmic improvements do not automatically translate to hardware performance, and unoptimized FlashAttention suffers from arithmetic overhead and the idealized memory model hits standard attention's bottleneck. And for the solution, once we co-design the algorithm with HLS, applying tiling, pipelining, and control unrolling, the algorithm's theoretical advantage becomes visible. This enables a 13.6 times reduction in latency. And second, the memory to compute transformation. A second important finding is that fundamental change in workload nature. FlashAttention converts quadratic memory usage into linear. This means edge device can now process long sequence without OOM failures typical in standard attention. We successfully transformed attention from a memory capacity bottleneck to a compute throughput bottleneck. And FPGAs are very effective at exploiting parallel compute. This is why FlashAttention becomes significantly faster when optimized. That's all. Thank you.